Welcome to today's lecture. This is Photoelectricity Part 4. In Part 4, we will be looking at numerical problems on photoelectricity. Numerical problems on photoelectricity. Let's look at problem number 1. Light of frequency 1.5 times 10 raised to the power 15 Hertz falls on a metal of work function 4.0 times 10 raised to the power minus 19 joules. Calculate the maximum kinetic energy of the emitted electrons. We're given the Planck's constant to be 6.63 times 10 raised to the power minus 34 joules second. Don't forget EK max, maximum kinetic energy, is the photon energy minus work function W naught. E, which is the photon energy, is HF minus W naught. We're given the work function directly, so we don't need to convert W naught to HF naught. But we're not given the photon energy directly. We're given the photon energy as the frequency of the incident light on the metal. So if we multiply the frequency of the incident light by the Planck's constant, that will give us the photon energy. So then 1.5 times 10 raised to the power 50, which is the frequency of the incident light, multiplied by Planck's constant, gives us the photon energy. Don't forget the work function is given as 4.0 times 10 raised to the power minus 19. And then if we resolve this appropriately, our maximum kinetic energy then becomes 5.95 times 10 raised to the power minus 19 joules. Question number 2. The threshold frequency of a metal is 5.5 times 10 raised to the power 14 Hertz. 5.5 times 10 raised to the power 14 Hertz. What is the work function of the metal? That's the first question. What is the work function of the metal? Number 2, that is the B part of the question. If light of wavelength 4.5 times 10 raised to the power minus 7 meters shines on the metal, calculate the maximum kinetic energy of the emitted photoelectrons in joules and electron volt. We are given certain parameters to work with. 1 electron volt is 1.6 times 10 raised to the power minus 19 joules. H, which is Planck's constant, is 6.6 times 10 raised to the power minus 34 joules second. The speed of light, which is 3.0 times 10 raised to the power 8 meter per second. Let's start the solution, the solving properly. We know F naught, that is the threshold frequency, is given in the question as 5.5 times 10 raised to the power 14 Hertz. The threshold frequency of a metal is 5.5 times 10 raised to the power 14 Hertz. So the threshold frequency is 5.5 times 10 raised to the power 14 Hertz. Planck's constant given is 6.6 times 10 raised to the power minus 34 joules second. So W naught is HF naught. W naught is the work function. And so if we multiply the Planck's constant by the work threshold frequency, that gives us the work function. Planck's constant, the threshold frequency, that gives us the Planck's constant. Look at question number 2b. If light of wavelength 4.5 times 10 raised to the power minus 7 meter shines on the metal, calculate the maximum kinetic energy of the emitted photoelectrons in joules and electron volt. Again, parameters given, we are given the wavelength of the incident light to be 4.5 times 10 raised by minus 7 meter. In the previous solution, we were given the frequency, so we use photon energy as HF. But here we are given the wavelength, so we convert this to HC over lambda. We have established this fact already, that F is C over lambda. And then put in our parameters, Planck's constant, speed of light, the wavelength, that gives the photon energy as 4.4 times 10 raised by minus 19 joules. Again, don't forget that our EK max is photon energy minus the work function. So EK max is 4.4 times 10 raised by minus 19 joules minus 3.63 times 10 raised by minus 19 joules. If you resolve this properly, you end up with 7.7 times 10 raised by minus 20 joules. Now, to convert joules to electron, you need to remember that they gave us a basis for our conversion, which is 1 electron volt is 1.6 times 10 raised by minus 19 joules. And so 7.7 times 10 raised by minus 20 joules times 1 electron volt over 1.6 times 10 raised by minus 19 joules. Arranging the whole system such that the joules cancels out, and then we have our electron volt. In other words, dividing the maximum kinetic energy in joules by 1 electron volt in joules converts it to electron volt as shown. This will take us to question number 3. Question number 3. A light of wavelength 5.0 times 10 raised by minus 7 meter is incident on a metal, resulting in photo emission of electrons. If the work function of the metal is 3.04 times 10 raised by minus 19 joules, calculate the A, frequency of the light, B, energy of the incident light, C, maximum kinetic energy of the photoelectrons, D, stopping potential. We're given the following parameters: speed of light 3.0 times 10 raised to the power 8 meter per second. Planck's constant to be 6.6 times 10 raised to the power minus 34 joules second, and the electron as 1.6 times 10 raised to the power minus 19 coulombs. So the first part of the question, the frequency of the incident light. We're given that light of wavelength 5.0 times 10 raised to the power minus 7 meter is incident on a metal. So the wavelength of the light shining on the metal is 5.0 times 10 raised to the power minus 7 meter. So then remember, C is lambda frequency. So we can get the frequency by saying C over lambda. And then we put up the necessary parameters, that the speed of light and the wavelength. That will give us 6 times 10 raised to the power 14 hertz. The B part of the question, energy of the incident light. Photon energy is HF, that is Planck's constant, times the frequency of the incident light. So E is HF. E is 6.6 times 10 raised to the power minus 34 times 6 times 10 raised to the power 14. If you resolve this properly, you end up with 3.96 times 10 raised to the power minus 19 joules. Question C, the maximum kinetic energy of the photoelectrons. EK max is E minus W. Of course, the photon energy is 3.96 times 10 to the power minus 19 joules. And the work function of the metal is given as 3.04 times 10 to the power minus 19 joule. If the work function of the metal is 3.04 times 10 to the power minus 19 joules, so then our EK max is 3.96 times 10 to the power minus 19 minus 3.04 times 10 to the power minus 19. If you resolve this properly, you will get 9.2 times 10 to the power minus 20 joules. D, stopping potential. EVS is EK max. And so our electron is given as 1.6 times 10 to the power minus 19 times the stopping potential, equal to EK max, which is 9.2 times 10 to the power minus 20. Eventually, EVS is 9.2 times 10 to the power minus 20 over 1.6 times 10 to the power minus 19. This will give us 0.575 volts. I urge you to attempt number 4. What does number 4 say? A certain metal has a work function of 2.5 eV, that is electron volt. Calculate A, the threshold frequency, B, the maximum kinetic energy of the photoelectrons, B again, the maximum kinetic energy of the photoelectrons when the metal is illuminated by light of wavelength 8.5 times 10 to the power minus 5 centimeter. Or given Planck's constant to be 6.6 times 10 to the power minus 34 joule second. C to be 3.0 times 10 to the power 8 meter per second. And 1 electron volt to be 1.6 times 10 to the power minus 19 joules. This brings us to the end of photoelectricity.